All right, here we are with problem set C. Actually, these are sample problems as opposed to the actual problem set itself. So this is kind of to build momentum into that problem set C, which will be in the classroom, of course, most likely as a PDF. In any case, this is just a running narrated video. I'll save it as a video. So you can mute, you can skip ahead, rewind, pause, do whatever you need to do just like the others in order to see the solutions, see the problems, and arrive at the understanding you need or to figure out what questions you have. And then you can certainly get with me and we can get those questions answered on a one-on-one basis, or if the class needs, we can Zoom. Okay, so this is a companion to an assignment that I have in the classroom on this problem set, sample set, practice. It's a running narration, of course, for all 5 problems. I would ask, that you just very much feel free to pause after each one. You can mute me certainly and just look at the solutions because the solutions are presented in totality once we get to that slide. So you can just see the flow of the problem, see the solution. I think in all but the last one, and I'll point that out. So again, what this is just to set you up for better success with the textbook problem set C out of chapter 4 and the worksheet problem set C as well. Okay, here we go. If you've already done the worksheet or if you've tried the first one, you'll realize that the first 3 are actually based on the blue whale. Here up on top, there's just some really, what I found was very interesting information about blue whales, things I did not know. And really what we're dealing with is the mass of a newborn. So we have this newborn, not very old, 3,000 kilogram blue whale. And this immature blue whale has become stranded on the shore, and we have rescuers that are going to pull it back out to sea. The information follows that we're going to hook it up with a special motorboat. We have a special padded cable so you're not injuring the whale. And we are going to pull the whale with 4,000 newtons. See, that's 4 kilonewtons. 4,000 newtons of force. In this case, we are assuming a frictionless beach. We're trying to figure out what the net acceleration of the whale is as it slides into the water. So that's the problem. And then if we set it up by grasp, it will look like this. So here is the total problem. And what I have here for the given is I have the applied force of 4,000 newtons. I have the mass of 3,000 kilograms. I will admit the 3,000 kilograms was to 1 sig fig, so your answer is, it's not very precise, but it is what it is. So here are my givens, and what the question is what is the net acceleration? Well, what I'm aware of is F net equals the applied force, because that's the only force that is actually acting on the whale, that's moving the whale. We can ignore the normal, we can ignore the force of gravity. They equal, they cancel. So then I can take that net force equaling the applied force, and then it's all equaling mass times the net acceleration. So F equals ma. That's the model right there. I've taken this model and rearranged it to solve for my unknown. The solve part is the actual plug and chug. Here's my 4,000 newtons. Here's my 3,000 kilograms. You do the division, and here is my net acceleration, and I just left it at 1.33. I did not round it to correct sig figs in this case. That was unintentional. I just wanted to get an answer down, but it would round to 1, and there you go. Now, how do the units work? Because I have a newton here and a kilogram there, and all of a sudden I end up with acceleration. Remember what a newton is. A newton is a kilogram meter per second squared. That right there is the newton. And then I'm dividing it by kilograms. So here's my kilogram. Kilograms cancel, leaving units that match what we expect for acceleration. And of course, if you're doing grasp, then you're going to take the answer with the significant figures intact, and you're going to put it back in context of the blue whale question. Okay, let's move on to C2. Again, if you have not done C2 yet, it's going to be a lot like C1, but a little bit more complex. So go on and try C2 on the other sheet, and then come back and check this video out. Or let me flip the slide. Here's the problem. You can simply pause at this moment and you can use this information and just solve it on a piece of scratch paper and then immediately check the solution. And in fact, you could do this for all 4 remaining problems. Okay, so what's different here? The whole top is the same because I'm dealing with the whale again. It's still a 3,000 kilogram newborn. Still stranded on the beach. Coast Guard is still going to come in and rescue it, and we're still using 4,000 kilonewtons of applied force. However, the beach will exert friction in this example, so the frictional force is going to be 10% of the baby whale's weight. Now, I would draw your attention to the fact that this is a mass, this is not a weight. Weight is a measure of force. This is a mass in kilograms. Weight is going to be measured in newtons. It's a force. So just, I think that's obvious, but in case it's not, because weight and mass, they are problematic terms when we're not in a science setting. We are talking weight here, so 10% of the baby whale's weight. Question here is, what's the net acceleration? So it's the same thing. Okay, there's the problem. You could pause and do your givens, do your, the whole grasp method or problem solving as you want to see it, and then come up with a solution. So let's check out the solution on the next slide. Here's the solution in totality. Here are my givens. I have the applied force of 4,000 newtons. I have the mass of 3,000 kilograms. And I have a frictional force, kinetic, because the whale is moving, so I just went ahead and labeled it kinetic, which is going to equal the weight, that's a W, equaling the weight multiplying by 0.1, which is 10%. So 10% of the baby whale's weight. Okay, the requested and required. Here is where we actually have more than what is requested. What is requested is the net acceleration. But in order to find that, I need to find the weight because I need to find the kinetic friction. So these are required in order to get to the requested. That's why that R has the requested and required. Oftentimes there are things that you just have to find out in order to get to what you're really targeting. Okay, well, what models do I know? Weight equals mass times gravity. So there's the weight right there. And then once I know that, the force of friction will simply take that weight and multiply it by the 10% in decimal form. Then down here I have my summation of forces. So the net force is equal to the applied force plus the force of kinetic friction. Remember, one of these will be negative, so technically they subtract from each other. Just be aware of that. They do not actually add together because one is always going to be opposite because it's a resistant force. And in light of the whole problem, it doesn't matter which one of these you make positive or negative. It really doesn't, as long as they're opposites. All of this is going to equal, again, ma net, mass times net acceleration, F equals ma. There you go, that's the whole thing. So then my rearrangement is the net acceleration is equal to summation of forces on top divided by the mass. I did not bother to do substitutions. I could take this and substitute it. I could take this and substitute it. So this could look a lot fancier, certainly a lot more complex. But I just left it simple because everything else is up here. Then here is the numerical plug and chug for the solve, the 4,000 newtons of the applied force. Here is calculating the weight of the whale. Here's the mass multiplied by gravity, the acceleration of gravity, and then multiplied by 0.1. So there's the 10% factors, and I've got that grouped in brackets. You add these together. Notice this one will be negative, so technically they'll subtract, and the answer will be smaller than 4,000 newtons for your numerator, divided by 3,000 kilograms equals, and then notice what has happened to the acceleration. With only 10% friction of the baby's weight, of course, it has gone from 1.3 meters per second squared down to 0.35 meters per second squared. Again, I'm not paying attention to sig figs. I should. I didn't for the purpose of just finding answers for this, but it would be 0.4 if you were doing sig figs. So yeah, friction. All of a sudden, that whale is moving much more slowly. The acceleration is certainly at a much lower magnitude. Okay, let's move on to the third problem. Okay, here's the third problem. The third problem is about the blue whale again, one more time with just one more layer of complexity. So, what do we have here? We have a pulling force. You can read all of this, and again, you could pause right now and you could actually go ahead and solve it and then come back and watch the rest of the solution to figure out what's going on. So we have a pulling force of 4,000 newtons. Remember, 4 kilonewtons is 4,000 newtons. The boat has a crane cabling system, and it's going to pull at an angle 20 degrees with respect to the water. If the frictional force is still 10% of the baby whale's weight, calculate the net acceleration again under these conditions. So there you go. Now we have some angle, well, not some angles, we have an angle involved, and what's going to happen? Okay, here is the solution. So my givens again, applied force. Force of kinetic friction is still that weight multiplied by 10%. I know it got a little messy there, but 0.1. The angle 20 degrees with respect to the water, and mass is still 3,000 kilograms. Requested and required. Got to know the weight so I can find the kinetic friction. And I have to know the applied force in the x direction. I know the applied force on the cable, but because it's now 20% at angle, or excuse me, it's 20 degrees on angle, I've got to ferret out the component to figure out how much of the actual 4,000 newtons is pulling the whale horizontally out into the ocean. So I've got to know that. Here's my force diagram just to show what I'm talking about. There's that 4,000 along the cable. Here is what the whale is actually going to do, and I've got to know that component there. And of course, the net acceleration, which is the point of the question. So these are required to get to the requested. Analyze. Here are my models. Well, weight is still mass times gravity, and that'll of course apply back into the kinetic friction. Net force is going to equal the applied force in the x direction, that's a component force, plus the kinetic friction force, which again, if you assign it negative, they'll subtract from each other. And this will all equal ma net. So force equals mass times net acceleration. It comes back to that. It's just in this net force, there could be a lot of things going on to make up that net force. Okay, rearrangement. Here's my rearrangement. Because I need to know the angle or the x value for the applied force, here is that model as well. I forgot to point that out. So the applied force in the x direction is the applied force multiplied by the cosine of the angle because of the way I have oriented my force diagram. Okay, well, then I've got the plug and chug, and I've actually done a little bit more as far as putting the substitutions in. All of this is your applied in the x, kinetic friction, multiplied by the mass, or divided by the mass rather, and that'll give you the net acceleration. Here's the plug and chug, 4,000 newtons cosine of 20 degrees plus 3,000 multiplied by negative gravity multiplied by the 10%. So that's where this value becomes negative and subtracts out of this value here, divided by 3,000 kilograms. Units will cancel correctly to give you an acceleration. And notice now we've gone from 0.35 down to 0.27, 0.3 if you're rounding to 1 sig fig because of the mass. Okay, so there you go. There's a level of complexity. Where's the complexity? It's in the net forces, where we have to figure out the net forces. We're summing the forces in order to figure something out. Okay, let's move on to the fourth question, which is not about a whale. Okay, so F equals ma again, Newton's second law. We have an elevator this time. This elevator is moving at a constant velocity. So at first, this is important information. 1.7 meters per second, going up with 2 passengers, guys named Gavin and Dan, I guess. Passengers have a combined mass of 156 kilograms. That's information. After constructing a force diagram, calculate the normal force the floor exerts on the passengers. So here's a kind of a little mini diagram of what's going on. There are not 2 people there, of course, but there should be. And it's moving in an upwards direction. Now, that's part A. Part B then sets up a situation to where the elevator, for whatever reason, starts accelerating upwards at 1 meter per second squared. Construct a new force diagram, calculate the new normal force as they begin to accelerate, and then there's a kind of a concept question. What do the passengers feel? Do they feel normal? Do they feel heavier? Do they feel lighter? Okay, let's move on. After you've solved this, move on to the solution. And I'll look at part A, then part B, although it might be a little bit choppy on the next couple of slides. Okay, so here is the solution for part A, where they're moving at constant velocity. Here are my knowns. constant velocity, so that is the velocity. Here's the combined mass. Looking for the normal force. Well, the normal force in this case is going to equal the force of gravity, which is the weight of them, so that's mass times gravity. So here's the combined mass multiplied by gravity. It comes up to be a negative value, and I've rounded that somewhat, so that might be correct sig figs there. I am not using the 1.7 meter per second velocity, so this is a 3 sig fig value. Now, the normal force is simply the positive value because the normal force is the restorative force in the up direction, whereas gravity is in the downwards. So they're equal and they're opposite, and this is at constant velocity, not necessarily at CV high school, because you're not allowed at CV high school at the moment. Okay, let's move on to part B. Okay, what happens when we are now accelerating? Okay, so net acceleration, besides the fact I know the other things, I know now the net acceleration, which is 1 meter per second squared up. I want to know the normal force and the applied force here. So the normal force plus gravity equals, sorry about the space here, that should be kind of squeezed together. Normal plus gravity equals the net force, which equals the mass times the net acceleration, so F equals ma. The net force is where, here's your complexity. And I don't think it's all that complex, but here is where we have to assume that there can be more than one force operating that we have to take into account. Well, the normal force plus the force of gravity, I can substitute in mass times gravity to know what the force of gravity is. And this equals ma net. So here are the models that I am using. Rearranging to solve for the net force, which is something I didn't do up here, so I just basically took this and rearranged it. So normal force equals the mass multiplied by the acceleration, so here's ma net, minus the mass multiplied by gravity, the weight of them. So this will be a negative value, and we are subtracting these two, so they actually will add together, which the normal force, if you think about it, if it's accelerating upwards, the normal force is going to have to do more work, if you will. It's going to have to do more in order to keep you from falling through the floor because you're accelerating upwards. So no surprise then that we went from 1530, I think, at constant velocity, now to 1690 at acceleration in an upwards direction. If you were accelerating in a downwards direction, this would be smaller than 1530. If this goes to 0, you are in free fall. The cable is snapped. Wow, it's kind of a movie scenario, right? So this is during acceleration up. And of course, they should feel heavier. If you've ever ridden in an elevator, just about everybody has. When it goes up, when it first starts out and you're accelerating upwards, you always seem to feel a little bit heavier. You feel it in your legs. Okay, that's number 4. Now, number 5 is, again, a completely different problem. So let's check number 5. Okay, here's number 5. Here's number 5, and number 5 is a kind of a trolley car that is on basically an inclined plane. So here's a diagram of it, and here's actually a historical picture of one showing how they had tram systems to get you up hills at various cities. So here's the information we're looking at. We're looking at an empty trolley car that has a mass. It's going to take a little under 6 seconds in order for it to go from 0 to achieve its final velocity. Its fastest velocity, if you will. And it's moving up a hill being pulled by a cable at 34.5 degrees. Okay, so we have information. Okay, the cable, able to exert a force of 2883.42 newtons up the hill. We have kinetic friction. Of course, the wheels are rolling, so I'm calling it rolling kinetic friction, but it's just friction. Between the rails and the steel wheels, it's only 3.4-ish newtons. There's more, you'll use all the numbers, but that's the magnitude. It's a very, very small magnitude with steel on steel rolling, not a lot of friction there. So determine the net acceleration of the trolley car over that initial period of acceleration from 0 to its maximum velocity that it'll obtain as it goes the rest of the way up the hill at constant velocity. Now, once we've done that, we have some additional things we can do. Determine the normal support force for the car on the rails. So we've got a car over here, it's on rails, and so there's a normal force, perpendicular of course, right? So it's going to be in that direction there. We want to calculate that. determine the final velocity of the car after 5.51 seconds of acceleration. So if we know the acceleration and we know the initial velocity is 0, we can go back to unit 3, which is acceleration, and we can grab some acceleration models and figure out this final velocity. Now, once it accelerates for 5.51 seconds and it's reached its maximum final velocity, if you will, so it's going to then travel at that velocity for the remainder of the trip, we want to determine the length of track that this car will travel at constant velocity if it travels for a little over a minute here, so 63.4 seconds, before slowing to a stop. Now, we're not going to worry about the slow to a stop. We're only worried about when it hits its final velocity after 5.51 seconds, it's going to travel for this amount of time at constant velocity, at whatever this velocity is. So as long as we know that, this is unit 2. So we have unit 4 and 5 material, actually. This is unit 5 as well if we're doing the modeling material. So unit 4 and 5 are here, and then we get actually into unit 3 and unit 2. So there's a lot of modeling going on right here. How do you solve it? Well, let's take this a little bit at a time. Here again, I would ask you, stop, try and solve this, and then check the solutions out as we go on. Okay, so this is the given and the requested. So here are all of my givens, and I'm not going to use all of these at once, but here are all my givens. I've got the mass, the angle, the time of travel to go from 0 to maximum velocity. I have the tension on the cable, I have the kinetic friction, and I do have the second time for constant velocity as it moves up the track then. My requested and required, I'm looking for the net force, the normal force, the final velocity, and the change in displacement, so the length of the track once it's a constant velocity. And I went ahead and reproduced a very rough but accurate, if you will, force diagram showing the car, normal force perpendicular, gravity on an angle to the rails, but of course perpendicular to the surface of the earth. We have kinetic friction down the ramp. We have the force of the tension of the cable up the ramp, so that's the applied force. And with gravity, gravity again doing two things. Gravity is also pulling this cart down the hill. Now the cable is able to overcome that, but gravity is making this cable do more in order to make that cart do what it does. So I have this X component of gravity pulling it down. Also, against the normal force, we have the Y component of gravity, which counteracts the normal force. That's what holds it to the rails. The rails then establish the normal force up. So that's what we have. Let's move on to the analysis phase where we present the models that we'll use. Okay, in sequence. If we are looking for the net acceleration, which is the first thing, okay, well, the net force equals the mass times the net acceleration. Okay, F equals ma. Well, the net force is a combination of several forces. Well, what forces are they? We have the applied force in the x direction. That is the tension on the cable in the up direction. So that's the cable. We have gravity in the x direction pulling down, and we also have kinetic friction pulling down. That's a very bad K, but that's a K for kinetic friction. Okay, gravity in the x direction is actually, it's a component force. And so the way I set the previous force diagram up, it's a sine function for me. So the x component of gravity, which is countering some of the cable, is force of gravity overall multiplied by the sine of the angle. The force of gravity here is the mass of the trolley car multiplied by the gravitational acceleration, or the gravitational field strength, if you will. So this then expands to mg. So fg of x equals mg sine of the angle. And I've got all that information. So if I pull it all together and then I resolve for the net acceleration, this is what I get. Tension in the cable, which is the applied force in the x direction, plus the kinetic friction down the ramp, plus the gravity pulling down the ramp. This will be negative, this will be negative because they're pulling down the ramp, this is going up the ramp, so we'll just make that positive. You put all those together, divide it by the mass, that should give you the solution. Now, of course, this is the analysis phase, so there is no plug and chug here. What about the normal force? Well, the normal force is simply countering the gravitational force in the y direction. The y direction of force of gravity is again, it's a component force, and so mass gravity times the cosine of the angle. Refer back to my force diagram if you are interested in the trig and how I got it to be the cosine. You plug and chug there because we have the values, and you'll find the normal force, remember, which is just opposite. So if this comes up to be negative, normal force is positive. What about that final velocity? Well, with the final velocity, remember that the initial velocity was 0 when the cart started to be pulled up the hill, and we now know the net acceleration because we found it right here. So that's going to come down here. It's now known information. The time was given at 5.51 seconds, I think. And so you plug and chug there, and you've got the solution for the final velocity. Units should all work out, of course, to be meters per second. And then lastly, we have 63.4 seconds at constant velocity. Whatever the final velocity is the constant velocity it will have all the way up the tram for whatever this distance is. So that's just this velocity as constant velocity multiplied by the time. You do that, you now have the displacement over that period of time. Okay, the next slide, which I believe is the last, is the just the numerical solutions, and here we go. Okay, on this one, because I was running out of room as I was writing on a tablet over a PDF with like an overlay, I just didn't have a lot of room to go and do the whole plug and chug. So if you want to see the actual plug and chug, email me, let me know or whatever, and I can work it out on a sheet of paper, show you where all the numbers go, and I can take a picture of it and send it back out or post it. It's okay. But in any case, if you plug and chug, we know these numbers, and you do that, you're going to solve, and you're going to find that over the first 5.5 seconds, the trolley car has an acceleration of just a little over 1 meter per second squared in the up direction. What is the normal force? Well, it's countering the force of gravity in the y direction, which is a component force, and that turns out to be 3,436 newtons, and I am right now just ignoring sig figs to get an answer down. I would round it going back, taking a look at the values used, and then I would round it accordingly. What about the final velocity? Initial is 0. We knew the acceleration here, so that 1.09 comes down here. I multiply it by that the 5.51 seconds, I think, is the number, and that comes up to be 6.006 meters per second. Again, ignoring sig figs for the moment just to get an answer. Then finally, what about the displacement once it attains this velocity? Well, how far can it go at that velocity for 63-ish seconds? So velocity multiplied by time, this is what we would then, I'm sorry, that's not even the solution. This is the model we used, and this is the solution. Turns out that it would go 380.8 meters over that period of time at that velocity. So, Unit 4 material, Unit 4 material, Unit 3 material, Unit 2 material, all working together with this tram. So very interesting. Now there is one last slide, and it's just a photograph. There's nothing to do with it, but here we go. Okay, so here's a photograph. Now that tram that you are looking at certainly is not almost 400 meters long. So this is not exactly that particular that model or that situation. This is an actual historical photograph, late 1800s in Cincinnati. You can look these images up yourself for this particular trolley car system. But they were, I have no idea how about widely used they were, but certainly a realistic situation, even though as the situation was presented in a physics scenario, it might not seem as likely, but here is a real situation that you can see how the trams might work. Pretty much a trolley car just loaded onto a tram, hoisted to a higher elevation, and then this actually looks like it would simply drive off and keep on going, as opposed to, and it would be electrified, so it would actually be an electric trolley. Here's some electrical contact points up here that would contact the overhead wires. So this is not simply just a car that moves people up and down. This is actually a trolley system that moves trolley cars up and down, and then the trolley car would then move off. So very interesting. Okay, there you go. That's it. With all of this, if you understand it, great. Move on to problem set C. And if you don't, look back over it again, try them again, and certainly get in contact with me, and I'll answer whatever questions you have. Thanks.